NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth.
Far beyond the orbit of Neptune, a faint signal whispers through the dark. It travels for nearly 20 billion kilometers before the giant dishes of NASA's Deep Space Network catch it. A fragile stream of data proving that Voyager 1, the most distant human-made object, is still alive. For months, the spacecraft had spoken in nonsense, its telemetry garbled as though the void itself had scrambled its thoughts. Engineers on Earth held their breath, and then suddenly order returned. The probe began sending usable information again, like a lone lighthouse beam sweeping across the cosmic ocean. But the revival of Voyager 1 is only part of the story. Its twin, Voyager 2, broke through the edge of the solar system and saw something no one predicted. Beyond the planets, past the icy Oort cloud, it found hints that our entire solar system might be floating inside an immense cosmic bubble. A structure so vast and mysterious it challenges everything we thought we knew. When Voyager 2 crossed that final boundary, its instruments recorded events that left scientists stunned. The steady plasma wind from our sun disappeared. Charged particles shifted direction. Magnetic fields twisted as though shaped by an unseen hand. Was it a wall, a shield, or something more enigmatic, perhaps even alive in a way we can barely imagine? What Voyager 2 witnessed changes how we think about our place in the galaxy. And to understand the magnitude of those revelations, we have to follow the story from the beginning, back to an era when humanity first dared to send emissaries on an interstellar odyssey. In the mid-1970s, our knowledge of the outer solar system was hazy at best. Jupiter loomed as a giant blur in telescopes. Saturn's rings were beautiful but indistinct, and the ice giants Uranus and Neptune were mere points of light. On 20th of August 1977, NASA launched Voyager 2 to change that picture forever. And just weeks later, on 5 September, its sibling Voyager 1 followed. Voyager 1 was built for a mission no one had attempted. A journey of more than 4 billion kilometers through unexplored space. From the start, engineers designed it to venture far beyond the familiar neighborhood of Earth and to keep going, past the protective bubble of the sun's influence and out into the raw expanse between the stars. Few expected that decades later it would still be operating, still sending messages home. Yet even in those early days, the people who assembled the spacecraft sensed they were building a messenger capable of outliving them all. Years later, when Voyager 2 approached the very edge of the sun's domain, its sensors recorded a cascade of surprises. Solar wind particles, charged streams of plasma that normally race outward, suddenly dropped to almost nothing. At the same moment, energetic cosmic rays from interstellar space surged. Magnetic field lines shifted in ways scientists had never modeled. These weren't subtle blips. They were clear signs that the probe had crossed into a region no human instrument had ever sampled. This boundary is called the heliopause, the skin of the sun's protective bubble. Crossing it means leaving the heliosphere and stepping into interstellar space, a realm shaped by the galaxy itself rather than our star. Voyager 2's data forced researchers to rewrite textbooks on how our solar system interacts with the Milky Way. Back in 1977, the dream was simply to reach the outer planets. Voyager 2 was meant to perform a grand tour. Jupiter, Saturn, Uranus, and Neptune in one sweeping arc, exploiting a once-in-175 years planetary alignment. But planners quietly designed for something more. They gave the craft a nuclear power source that could last decades, built redundant systems, and encoded commands that future generations could send across unimaginable distances. Today, Voyager 2 has traveled roughly 20 billion kilometers from Earth, a feat unmatched by any other functioning spacecraft except its twin. These numbers aren't just statistics, they're a testament to human ambition, to the belief that curiosity can outlast lifetimes. Voyager 1, though launched after Voyager 2, was actually intended to outpace it. The September 5th launch from Cape Canaveral set it on a faster trajectory, ensuring it would pass Jupiter and Saturn first. The reason for sending two probes was simple yet brilliant. The rare alignment of Jupiter, Saturn, Uranus, and Neptune allowed slingshot maneuvers from one planet to the next, saving fuel and decades of travel. If one spacecraft failed, the other might still complete the mission. Together, they carried humanity's curiosity and a golden calling card, the famous Golden Record, etched with sounds of Earth, greetings in dozens of languages, and music from across cultures. These were not just scientific instruments, but ambassadors, bearing the story of a small blue planet to whoever might someday find them. Voyager 1 was a marvel of 1970s engineering, a compact observatory packed with sensors and cameras. High-resolution imaging systems captured planets and moons in vivid detail. A radio science package measured planetary gravity and atmospheres. Infrared and ultraviolet spectrometers gauged temperatures and chemical compositions. A magnetometer traced the invisible lines of magnetic fields, while a plasma spectrometer and low-energy charged particle detector probed the dance of ions and electrons. To communicate across the abyss, NASA relied on the Deep Space Network, 3 massive antenna complexes positioned 120 degrees apart in Spain, California, and Australia. This global trio ensured that as Earth rotated, at least one station could see Voyager at all times. Even now, each whisper from the spacecraft takes more than 22 hours to reach us, and engineers must aim the 3.7-meter dish on Voyager with incredible precision to keep that link alive. Decades after launch, Voyager 1 remains our farthest traveler. Engineers periodically upload software patches, power down non-essential systems, and adjust its antenna to conserve dwindling energy. The probe's radioisotope thermoelectric generators, fueled by plutonium, still produce enough electricity for a few instruments, but each year the power drops. Eventually the signal will fade, yet for now the spacecraft continues to send data from a realm where the sun is just another bright star. When Voyager 1 swept past Jupiter, it transformed our understanding of the giant planet. Through its cameras, we saw a world of swirling belts and zones painted in ochres and creams, an atmosphere alive with titanic storms. Jupiter's great red spot, long visible through telescopes, revealed itself as a colossal hurricane wider than Earth, spinning for centuries. Then came lightning. Instruments picked up radio emissions known as whistlers and captured fleeting flashes of light on the planet's night side, the first proof of lightning beyond Earth. The most breathtaking discovery, however, erupted from Jupiter's moon Io. Voyager's images showed towering volcanic plumes, fountains of sulfur dioxide and molten rock reshaping the moon's surface in real time. This was the first confirmed active volcanism on another world. Voyager also spotted 2 new tiny moons, Thebe and Metis, adding to Jupiter's crowded family. Looking back toward the sun, it detected a faint dusty ring around the planet, ending the belief that Saturn alone wore such adornments. The spacecraft mapped Jupiter's powerful magnetosphere, revealing radiation belts far stronger than scientists had guessed, regions so intense they would fry unprotected electronics. And it gifted humanity detailed portraits of the Galilean moons. Europa's smooth, crack-scarred ice hinting at a hidden ocean, Ganymede's patchwork of craters and grooves, Callisto's ancient battered surface, a relic of the solar system's violent youth, and the irregular Amalthea, a small potato-shaped world unlike anything seen before. Each observation reshaped theories of planetary formation and ignited plans for future missions. On 12th of November 1980, Voyager 1 executed a daring flyby of Saturn, swooping within about 124,000 kilometers of the planet's cloud tops. From that vantage, it uncovered a realm as complex as it was beautiful. Saturn's atmosphere turned out to be unlike Jupiter's. Instead of the expected helium-rich mix, it was mostly hydrogen with only about 7% helium, evidence that heavier helium might be sinking toward the planet's core. Voyager revealed intricate banding in Saturn's cloud layers and immense storms that circled the planet like slow-motion hurricanes. Its cameras captured the majestic rings in unprecedented detail. What looked from Earth like solid bands resolved into countless icy particles and thin, ever-shifting gaps sculpted by the gravity of small shepherd moons. The probe discovered new ringlets and revealed spokes, mysterious radial markings that seemed to appear and vanish. Saturn's moon Titan proved especially tantalizing. Voyager's instruments detected a thick nitrogen atmosphere laced with methane, suggesting chemical processes that might resemble those on the early Earth. The haze was so dense that the surface remained hidden, but scientists knew they had found one of the most intriguing worlds in the solar system, a target that would later inspire the Cassini-Huygens mission. From Saturn, Voyager 1's trajectory carried it out of the plane of the planets and toward interstellar space, while Voyager 2 continued on to Uranus and Neptune. Both spacecraft, however, would eventually confront the boundary of the Sun's influence and step into the greater galaxy. Today, more than 4 decades after launch, the Voyagers keep traveling. They have outlasted their creators and become silent envoys of Earth, each carrying the golden record, a message of music, mathematics, and greetings meant for any distant intelligence. Whether or not anyone ever finds them, they embody the restless curiosity of a species unwilling to stay home. Every faint transmission from these ancient machines reminds us that exploration is not a single moment, but a continuing act of faith. The Voyagers prove that even from a small world around an ordinary star, humanity can send its voice across the cosmic ocean and be heard. After parting ways with its twin, Voyager 2 set a course few imagined possible. On 24 January 1986, it became the first, and still the only, spacecraft to visit Uranus. The planet, a pale cyan marble tipped on its side, defied expectations at every turn. Voyager 2 revealed a world with an axial tilt of 98 degrees, rolling around the sun like a ball spun on its side. Its atmosphere, largely hydrogen, helium, and a dash of methane, produced high-altitude haze and unexpected wind patterns. Temperatures plunged to a frigid 224 degrees, making Uranus the coldest planet measured in our solar system. The spacecraft discovered 10 new moons, including Puck and Juliet, and detected 2 faint rings composed of dark material, a far cry from Saturn's glittering bands. Magnetic field measurements were the biggest shock. The field was sharply tilted relative to the planet's rotation axis and offset from the center, creating a lopsided magnetosphere that no model had predicted. These findings forced planetary scientists to rethink how magnetic fields can form and behave, demonstrating once again that each stop on the Grand Tour rewrote textbooks. 3 years later, on 25 August 1989, Voyager 2 reached the solar system's final giant, Neptune. The deep blue planet greeted the spacecraft with fierce winds, the fastest ever recorded in the solar system. Screaming across the atmosphere at over 2,000 km/h, Voyager 2's cameras revealed the Great Dark Spot, a massive storm rivaling Jupiter's Great Red Spot but with a dynamic lifespan, appearing and disappearing in a matter of years. Methane-rich clouds streaked the skies, and unexpected heat signatures suggested internal energy sources still churning within the planet. Perhaps the most dazzling find lay in Neptune's moon Triton. The probe captured images of active nitrogen geysers erupting kilometers high, a frigid world with a tenuous atmosphere and surface temperatures near 235 degrees C. Triton's retrograde orbit hinted that it was likely a captured Kuiper Belt object, offering clues about the chaotic early solar system. Voyager 2 also charted 6 new moons and confirmed a delicate ring system of dark, clumpy arcs that defied simple gravitational explanations. With Neptune behind it, the spacecraft had completed humanity's first and only in-person survey of all 4 giant planets, a triumph that remains unmatched. With the planetary tour complete, both Voyagers turned their instruments toward the far frontier. The sun grew fainter, the planets mere points of light. Cosmic rays, magnetic fields, and plasma densities became the primary data as the craft pressed outward. Voyager 1 crossed the heliopause in August 2012, while Voyager 2 followed in November 2018. Each crossing delivered a wealth of measurements about the interaction between solar wind and interstellar medium. The probes revealed that the heliosphere forms a complex, layered boundary rather than a simple bubble, with regions where charged particles pile up like waves against a shore. Even at these staggering distances, mission engineers maintained contact, sending occasional commands and receiving faint signals that must traverse nearly a full day to reach Earth. Both Voyagers carry a 12-inch gold-plated copper disc, the Golden Record. Conceived by a team led by Carl Sagan, it contains music from Bach to Chuck Berry, greetings in 55 languages, sounds of Earth, from thunder and birdsong to a baby's cry, and a pictorial guide explaining how to play it. The record is both a time capsule and an interstellar greeting card. Should an intelligent civilization ever intercept one of the spacecraft, they will find a snapshot of life on our planet in the late 20th century. The odds of discovery may be slim, but the gesture is profound, an acknowledgement that we are not only explorers but also storytellers, eager to share who we are. The Voyager's findings continue to influence modern space science. Their observations of magnetic fields shape models for exoplanetary systems. Data from their interstellar crossings inform research on how stellar winds carve bubbles in the galaxy. Even missions like Juno at Jupiter or Cassini at Saturn owe part of their mission design to the groundwork laid by Voyager's early reconnaissance. The spacecraft themselves have become symbols of human perseverance. Universities teach engineering students lessons from their redundant systems and long-duration operations. Astronomers use Voyager data to compare our heliosphere to those around other stars, giving context to the search for habitable exoplanets. Power levels drop a little more each year. Engineers have already shut down many instruments to conserve the remaining electricity from the plutonium-powered generators. By the mid-2030s, the probes will likely fall silent. They will continue to drift, dark and inert, for billions of years, still bearing their golden messages, still tracing orbits through the galaxy. When that day comes, the last faint signal will not mark an end but a continuation. Voyager will keep traveling among the stars, a silent testament to a species that once looked at the night sky and decided to go. Long after their power fades, the Voyagers will continue to coast around the Milky Way. Calculations show Voyager 1 will glide within 1.6 light-years of the star Gliese 445 in about 40,000 years, while Voyager 2 will pass near Ross 248 in roughly the same epoch. They won't come close enough to disturb any planetary systems, yet their silent journeys transform them into artificial comets, tiny ambassadors tracing invisible paths through interstellar space for eons. Over the next few billion years, gravitational nudges from passing stars and the gentle pull of the galaxy's spiral arms will carry each probe on an unpredictable odyssey, perhaps even ejecting them into intergalactic space. Even as the instruments wink out, scientists continue mining decades of stored readings. Voyager Plasma Data Guide research into how our heliosphere shields Earth from cosmic rays. Magnetic field measurements refine models of galactic radiation, critical for protecting astronauts on deep space missions. The probe's precise tracking also tests general relativity over immense distances. Every archived byte remains a scientific time capsule, allowing future researchers armed with new theories to reanalyze and perhaps uncover insights we can't yet imagine. The Voyagers have inspired a new generation of interstellar concepts. NASA's Interstellar Probe Study envisions a craft launched in the 2030s capable of reaching 1,000 astronomical units in 50 years, 5 times farther than the Voyagers today. Private initiatives like Breakthrough Starshot dream of sending gram-scale laser-pushed sails to nearby stars within decades. Engineers planning these missions constantly reference Voyager's lessons on longevity, redundancy, and the art of communicating across unimaginable distances. Each design begins with the question, how did Voyager endure so long and how can we push even farther? Voyager has seeped into music, literature, film, and philosophy. Carl Sagan's famous pale blue dot image, captured as Voyager 1 looked back toward Earth in 1990, reframed humanity's perspective on its tiny home. Musicians sample the probe's electromagnetic sounds in ambient tracks. Novels and movies, from science fiction epics to intimate dramas, use Voyager as a metaphor for loneliness, curiosity, and hope. The spacecraft are not only machines of science, they have become shared symbols of endurance and the longing to connect across cosmic gulfs. Voyager's long flight also shapes conversations about planetary protection and cosmic responsibility. By sending an object carrying earthly microbes, however few, into interstellar space, humanity made its first physical mark on the galaxy. This raises questions. What obligations do we have as cosmic travelers? How do we preserve the pristine nature of distant worlds while still exploring them? International policies now grapple with these issues, drawing from Voyager's precedent as the first emissary beyond the Sun's domain. In the unimaginable far future, when continents shift, oceans recede, and even the Sun ages into a red giant, the Voyagers will still roam. They may outlast Earth itself. If intelligent beings encounter them millions or billions of years from now, the golden record could be the last surviving testimony of our species. Whether or not anyone ever listens, the act of sending it affirms a belief that knowledge, art, and curiosity deserve to travel beyond the limits of our own survival. As astronomers catalog thousands of exoplanets, Voyager's interstellar data provide a priceless baseline for comparing other stellar environments to our own. Measurements of the interstellar medium's density, temperature, and magnetic fields allow scientists to predict how other stars carve their own protective bubbles. By matching Voyager's readings with observations of distant astrospheres, researchers can estimate how common life-friendly environments might be throughout the galaxy. The little probes, therefore, act as scouts for worlds we have yet to find. With each kilometer traveled, Voyager extends the map of human knowledge. Its trajectory, carefully tracked over decades, refines our understanding of the Milky Way's gravitational landscape. Tiny perturbations in its path help detect subtle tugs from unseen masses, whether dark matter concentrations or distant objects in the Oort cloud. These data complement observatories like Gaia, turning Voyager into a moving beacon that helps chart the three-dimensional shape of our galactic neighborhood. Few scientific missions have spanned as many human lifetimes. Engineers who uploaded the first commands in 1977 passed the torch to younger colleagues who were not yet born at launch. Each new team inherits decades of notes, troubleshooting lore, and an almost familial attachment to the spacecraft. Voyager has become a living classroom in patience and continuity, teaching that exploration is not a sprint, but a relay in which each generation carries curiosity a little farther. Voyager forces us to ask profound questions. What does it mean to be known in a universe so vast? How do we define home when our artifacts travel forever? Philosophers and theologians cite the mission as evidence of humanity's need for meaning beyond survival. The Golden Record's inclusion of music and greetings rather than just data underscores that our identity is more than science. It is emotion, culture, and wonder. The drive to keep Voyager alive has yielded unexpected benefits closer to home. Deep Space Network upgrades improved Earth-based radio technology, influencing everything from GPS timing to medical imaging. Techniques for handling faint signals across light-day distances now inform communications with Mars rovers and future Moon-to-Earth relays. In pushing the limits for a far-flung spacecraft, engineers also advance the infrastructure that serves billions of people on Earth. Inspired by Voyager, scientists dream of the next great emissary. Concepts include fusion-powered probes, solar sail craft propelled by giant lasers, and miniature chips riding on beams of light. These designs aim to reach nearby stars within a human lifetime, carrying updated time capsules of art and knowledge. Each proposal begins with a nod to Voyager, acknowledging that our first attempt set a standard of durability and vision that future missions must match. As Voyager drifts deeper into the galaxy, it continues to sample the vast interstellar medium, an ocean of tenuous gas, plasma, and dust that threads between the stars. Every shift in particle density or magnetic orientation helps astronomers refine their models of how galaxies breathe and evolve. Each data packet from the spacecraft is a direct touch of that environment. A whisper from a place no other probe has yet explored. Voyager's magnetometer readings hint at a colossal magnetic lattice spanning the Milky Way. Scientists combine its measurements with radio astronomy to trace currents that may guide star formation and influence cosmic ray traffic. By comparing those readings with observations from pulsars and distant quasars, researchers piece together a portrait of the galaxy's hidden scaffolding, a structure that could shape the orbits of stars and even our solar system's distant future. While the probes were never built to find life, their journey fuels the quest for it. By demonstrating that a small craft can survive decades in deep space, Voyager laid groundwork for missions that might one day deliver instruments to the icy oceans of Europa or the methane seas of Titan, worlds it first revealed to be compelling targets. Its golden record also stands as an open invitation, a declaration that intelligent life on Earth is eager for cosmic conversation. From symphonies to sculpture, Voyager continues to inspire. Visual artists create installations that translate its data into color and light. Poets borrow its trajectory as metaphor for love and exile. Filmmakers weave its lonely passage into narratives of perseverance and discovery. Decades after launch, the probe has become a muse for creators who see in its endless journey a reflection of humanity's own search for meaning. Classrooms around the world still replay Voyager images to spark young imaginations. Universities use its mission logs to teach orbital mechanics, communications engineering, and project management across generations. International teams coordinate to keep the Deep Space Network listening, proving that curiosity transcends borders and politics. Voyager reminds us that knowledge belongs to everyone willing to look up. Long after our species is gone, Voyager will carry an uncorrupted record of a distant epoch. The golden record's copper and gold plating can survive for billions of years in interstellar cold, its grooves preserving the heartbeat of a world that once thrived around an unremarkable star. Even if no one ever plays it, the record affirms that we once reached beyond survival to share our music, our greetings, and our wonder with the cosmos. Voyager now rides the Milky Way's slow rotation, circling the galactic center once every 225 million years. Its path will weave through regions of varying density, thin hydrogen clouds, dark molecular knots, and pockets of cosmic rays. Each encounter subtly alters its velocity and heading, making the spacecraft a silent participant in the grand galactic dance. Astronomers have calculated that in about 40,000 years, Voyager 1 will pass within 1.7 light-years of the red dwarf star Gliese 445. Much later, it will drift near other faint suns, perhaps skimming the outskirts of future planetary systems. Though its instruments will long be silent, its metal hull will carry the marks of micrometeoroid impacts, an ancient traveler crossing the tides of interstellar time. If another civilization someday intercepts the probe, they will find the golden record, instructions etched in symbols to play its analog sounds, the greetings in 55 languages, the music of Bach and Chuck Berry, the sounds of Earth's wind and surf. These could become the first evidence another species has of humanity's brief moment in the cosmos, Voyagers. Long Trek has already informed the design of proposed interstellar missions such as breakthrough starshot and fusion-powered craft. Engineers analyze how its power systems aged, how its instruments endured cold and radiation, and how its trajectory evolved. Applying those lessons to future probes that might one day reach Proxima Centauri within a single human lifetime. 5 billion years from now, our sun will swell into a red giant. By then, Voyager will be tens of thousands of light-years away, still intact if it has avoided collisions. It may outlast our planet, our oceans, even the sun itself, a solitary relic of a species that once looked to the stars. Eventually, the spacecraft's power will fail entirely and its transmitter will cool to the background temperature of space. Drifting in perfect darkness, it will become an inert but enduring monument, a fragment of human craftsmanship traveling endlessly through the void. Unseen but unforgotten, Voyager's greatest discovery may be what it teaches about us. It shows that curiosity can outlive politics, that imagination can cross eons, and that even a small planet's inhabitants can launch an idea into eternity. Long after our cities crumble, Voyager will continue its mission, to carry the story of Earth into the infinite night.